Welcome everybody to this HILT CRC webinar. I will give it a few moments while people arrive before I launch into the official welcome. Please do enjoy the webinar. Okay, I think our numbers have stabilized somewhat, and we are a few minutes past half past, at least on Canberra time. So my name is Fiona Beck. I'm an associate professor at the School of Engineering at the Australian National University, and I am also the research lead of Program 3 of the HILT, which is the Facilitating Transformation Program. And welcome to our HILT CRC webinar. It's wonderful to have with us today two great speakers talking on novel technologies to lower the cost of renewable hydrogen. So within the context of the HILT, focused on decarbonising heavy industry, hydrogen is a big part of our research interest. It is a really important potential energy carrier, but also a potential feedstock for reduction reactions. And as I'm sure everyone's is aware, often gets discussed in the media. And somewhat to my surprise, I'm always amazed at how much emotion can be produced by the talk of hydrogen in the media. People always seem to have very strong opinions. So we're bombarded by discussions about the potential of hydrogen as a future energy vector. And one side seems to think this is somewhat inevitable, whereas there are many people who really see a huge challenge in bringing down the costs of hydrogen sufficiently for it to become a real energy vector in the transition. So we hear a lot about renewable hydrogen as hydrogen that is generated through an electrolyzer powered by renewable energy. Today, we're going to look beyond that and talk a little bit about technologies that could potentially significantly lower the cost of renewable hydrogen. So not just continual reduction in costs of electrolyzers and renewable energy plant, but real step changes in the approaches. So before we jump into the main event today, I would like to acknowledge the traditional owners on the land which everybody is sitting nationally, but particularly to those of the land on which I am, which is the Ngunnawal people. I extend that respect to Aboriginal and Torres Strait Islander people here today as well. So I will jump straight into introducing our speakers after a few minor housekeeping issues. First of all, I'd like to just acknowledge that we have Susan Greaves joining us, who is the director of the HILT, the chair of the board of directors of the HILT. So welcome, Susan. And also just request that if you have any questions, please do put them in the Q&A during the presentations, and we will have a question and answer session at the end. So our speakers today, we have Professor Greg Mehta, who is the Professor of Chemistry and the Acting Director of the Centre of Energy Technology at the University of Adelaide. He has a number of really important other roles and responsibilities, and his work is focused on using light to produce chemical fuels, including hydrogen. We also have Vinod Gopalan, who has over 20 years experience working in the design, engineering, construction of large gas and coal-fired power plants, and has significant recent experience in energy from waste and green hydrogen development. So very much looking forward to hearing from both of them. And I believe we will start with Greg. If Greg, you would like, I will stop sharing my screen and I will ask you to share yours if you have slides to share with us.
I certainly do have slides. Thank you very much for the introduction, Fiona. So yes, title slide, as Fiona has already indicated, I am associated with a number of bodies that are involved with hydrogen production, and these are all the non-traditional routes, so not involving electrolyzers, and they all tend to be involving the direct route of photons to molecules. But today I'm going to be specifically just talking about hydrogen. Some of these entities that I'm involved with, I will be touching on. For example, I will be talking about the Centre for Energy Technology, the Global HILT Centre, and also talking about Spark Hydrogen as well, and that's Vinod's association as well. Why are we not advancing here? There we go. Okay, so Centre for Energy Technology, maybe people associated with the HILT aren't aware, but the reason for the HILT coming into existence was because of one of the forums that was established at the Centre for Energy Technology. That was the High Temp Forum. It was started in September 2018, and it runs every 2 years. And I know that planning has already started for the 2026 event. But alternating with that has been a series of forums focused exclusively on hydrogen production technologies. And you can see that these are in the interleaving odd years. And the next one, the fourth in the series, is going to be occurring in October of this year. And towards the end of my presentation, I'll just be reminding everybody of that. So I mentioned that out of the High Temp Forum sprung it laid the groundwork for the HILT CRC, but also the HILT Forum actually set the groundwork for the establishment of this global centre HILT, which is being funded in Australia through CSIRO and is also funded in the US, UK and Canada as well. On the HILT Centre, we have an annual meeting. I just returned from one a month ago that was held in the UK. And this forum actually looks at 3 different types of of hydrogen technologies. One is electrolysis, the other is methane pyrolysis, and the other is photocatalysis. So I'll be spending most of today talking about photocatalysis, but towards the end I'll also be talking about methane pyrolysis and one other type of non-traditional hydrogen production technologies using thermochemical processes. Okay, so hydrogen. We hear a lot about it. Just want to set the ground rules, what we know about it. We actually use it in very large quantities. It's about just under 100 million tonnes per annum. It's used all over the world. The major uses are in ammonia, methanol production, and in refining, converting petrochemicals. The production of hydrogen accounts for 2.5% of global CO2 emissions, and that's primarily because the hydrogen comes from fossil fuels, so possibly steam methane reforming if it's from natural gas or coal gasification as well. Of all of that hydrogen, 100 million tonnes, only less than 1% of it comes from low emission sources, and therefore there's a need to come up with alternative low carbon routes for making hydrogen at scale and at cost. And those 2 features are very, very important. Okay, so I've got a reality check here. So as I've said, we're currently only producing 1 million tonnes per annum of low emissions hydrogen. If you look at the Global Hydrogen Review from the IEA, you can see that according to the current outlook, by 2030, we're going to be producing 49 million tonnes of it low carbon, if all the announced projects are realised. Even furthermore, if there's the net zero scenario, it's slightly even more ambitious by 2030, up to 65 million tonnes. 40% of demand will be from new applications. Now, there's been a lot of reality checks that's gone on perhaps over the past 8 to 12 months, and this, I think, most people are starting to revise these rather ambitious projections. But even so, if we look at the current outlook for 2030, only 3.4 million tonnes per annum are currently in construction or under financial decisions. And where is the rest of it coming? It's assuming that most of it's from electrolysis and some of it is from blue hydrogen, which has got carbon capture and storage on it. But as we've all been hearing in the news, the financial decisions on electrolyzer plants are continually delayed. So there's great doubt about how are we going to be able to produce anything close to this amount of low carbon hydrogen. So, said before, just touched on 96 million tonnes. We're producing about 3/4 of it is made by steam methane reforming. Importantly, the cost of that hydrogen through this process is somewhere between $1, $2.50 a kilogram, depending on where this is in the world. And this is why it produces about 2% of global CO2 emissions. Currently, electrolyzers have a cost of about $5 to $12 a kilogram. And this is the big problem. There's such a big mismatch now between this and the current cost. And the question that everybody's asking is, will the cost of green hydrogen decrease? And I've got very, very simple numbers here that if you want to make 1 kilogram of hydrogen, if you want to do it from the electrolytic route, assuming that you've got a electrolyzer that's 80% efficient, you will need 50 kilowatt watt hours for that. And assuming a very, very low electricity cost, I'm not going to go into projections of electricity costs, but at 3 cents a kilowatt hour or $30 a megawatt hour, that means that just to make that hydrogen, just to purchase that electricity for that 1 kilogram of hydrogen is already going to cost you $1.50. So the question is, or the possibility that I see is that there's an opportunity for a cheap direct solar to hydrogen route, and that's what this is all about. So according to the IEA, there's a number of zero CO2 hydrogen methods. There's the electrolyzer power route, there's the direct photon route, and that's what I'm going to be focusing on now, the so-called photoelectrochemical processes, where we use photons to directly split water into hydrogen and oxygen. And I'm going to touch later on about using heat as well. So I want to now I want you to get you to think about how we possibly do this with this direct photon to fuel route. So obviously, we can think about setting out photovoltaics and then using that energy or the electricity from the photovoltaics to drive an electrolyzer. It's possible to optimize that very efficiently by using, for example, triple junction photovoltaic cells to optimize the current flow. And you can set up a system, and people have done this, where you have solar concentration of 42 suns, you optimize everything, and you can get a solar to hydrogen efficiency of 30%. So this is very high, and this is in fact the record for this approach. So this is what we call PVE, integrating photovoltaics with electrolyzers. But I want you to now consider that instead of a photovoltaic module, I want you to consider if now one of those modules, one of the modules in the electrolyzers was photoactive. So this is what we call photoelectrochemical device, where either one of the anode or the cathode, or potentially both, are photoactive, and that's used to directly couple the incoming photons to the production of hydrogen and oxygen, or the splitting of water. So either or both can be photoactive. There's usually a membrane, but there doesn't need to be, to keep the product separated. And the device can also be biased so that the potentials don't need to exactly match the requirement to split water. So this is what we call photoelectrochemical device, or PEC for short. And if you work in this field, I strongly encourage you to read this recent personal perspective about photoelectrochemical devices. If you then integrate that even further so that you no longer have two distinct electrodes, you've now got everything happening on a particle, or what's called you get what we call photocatalysis, or particulate photocatalysis, or PC. And here this one particle does everything. It absorbs the light, It's a semiconductor, so it generates electrons and holes, and those electrons and holes are then separated on that particle where they drive the reduction and oxidation processes to produce hydrogen and oxygen. So use of a single semiconductor, you can use two to generate what's called a Z scheme. There is usually the addition of co-catalysts required to assist with this transfer of charges and to drive the chemical processes occurring at the surface. And the big difference is that between this and PEC is that the two molecules, hydrogen and oxygen, are produced on the same particle, and therefore you co-produce the two gases, so-called oxyhydrogen, and this requires downstream separation. So PEC and PC, and I'm just going to give you a short tour of the state of the art for both of these technologies here. But before I do, I just want to mention about what the maximum potential is, the theoretical limit. There's a nice paper that was published now almost 10 years ago that looked at these types of devices and identified that it's possible to fairly readily get something that's occurring at a solar to hydrogen efficiency of 15%. And ideally, it might even be possible to get up to 30%. A simple way of looking at this would be to consider the solar spectrum and to look at the number of photons as you go from the ultraviolet across to the visible and into the near IR, and to count up those photons to recognize that there's some energy lost when you use those photons to split water. And you simply, to sum them up, you make some simple assumptions about some losses, and you can get out, when you go out to 1,000 nanometers, which is the thermodynamic limit for splitting water, 1.23 volts, you get about 35% solar to hydrogen efficiency. So certainly, whichever way you look at it, a solar to hydrogen efficiency of 30% for direct solar to hydrogen is theoretically possible. And as you'll see in a moment, no materials are able to do that, but they are improving every single year. So let's have a quick tour of the state of the art for these devices. So for a PEC device, a few years ago, back in 2018, this very sophisticated architecture was developed. It came out of a JCAP facility based in the US, and they demonstrated a solar to hydrogen efficiency of just over 19%. And you can see that, look, it's got similar materials that you'd find in a triple junction photovoltaic, but they have really integrated that, or made that photovoltaic, converted into electrodes that can split water. However, more recently, this has now been scaled up, and some technology that started out of the University of Iowa and a company that's now formed called Sun Hydrogen have developed these devices where they've integrated everything into a series of dense nanowires made of photoactive heterostructures, and they are now constructing up to these units here that are now the size of a typical PV module. They've now gone into partnership with Honda and CTF Solar to start to develop, mass produce these. What you see there is that 1.9 square meter panel that was announced in June, and they've also recently announced that they're looking at building a 30 square meter pilot plant. So this is one company definitely to keep an eye out there. There's their website there. Even more recently, people have started to now combine inorganic materials with organic materials. Those of you familiar with the photovoltaic world might be familiar with the idea of organic photovoltaics. The same sort of molecules that are used in those have now been integrated into this device. This is work that's come out of Imperial College London, and this paper was published just early this year. Dr. Salvador Eslava, so I had the pleasure of meeting him when I was in the UK last month, and he's developed this organic-inorganic integrated photovoltaic module, and he's demonstrated this has an efficiency of a solar to hydrogen efficiency of 5%. So that's PEC. What about for photocatalysis now? Well, the state of the art, at least for scale up, is my collaborator in Japan, Professor Kazunari Domin. He has developed these photocatalytic sheets. You can see them laid out here. This is the plant that's 100 square meters in scale. These particulate photocatalysts are based on a material, strontium titanate. which means that it is limited in the amount of solar light that it can absorb. It's only UV active. And although intrinsically has a very high quantum efficiency, so its efficiency that it can convert incoming photons to hydrogen and oxygen is close to 100%. The downside is because it's only UV active, its solar to hydrogen efficiency is less than 1%. But what this has done is demonstrated a couple of things. It's demonstrated scalability. These panels have been proven to be very durable, having a lifetime of about 1,300 hours, and even higher. It just drops about 20% over that period of time. And it also highlights the way that we can build the architecture for these devices, the molecular architecture, to enable us to get these highly efficient devices. And then we have a different approach, but still making what I'd call particulate photocatalysts, is Professor Zech and me out of the University of Michigan has developed photocatalysts that are based on nanowires made by molecular beam epitaxy of a 3,5 semiconductor. It's gallium nitride base. It's doped with indium to allow it to absorb visible light. And it has a reported solar to hydrogen of 9%. They've even demonstrated this operational with seawater, where it's slightly less, about 7% solar to hydrogen. And this technology has been licensed to NX Fuels for commercialization. And this technology is what the group working on photocatalysis, which I lead in Australia, is working to improve. So this work is associated with the HILT Global Centre. So you can see that there's definitely been this improvement of solar to hydrogen efficiencies, and it now has got to the point where these things are starting to make commercial sense. As you've seen, there's a couple of startup companies, NX Fuels and also Sun Hydrogen. My group started getting interested in photocatalysis about 15 years ago. We took a different approach where not only were we interested in this direct photon to molecule process using photons, but we also wanted to utilize the heat as well. So we wanted to combine or use the full solar spectrum to see if we can more efficiently split water into hydrogen and oxygen. So using the entire solar spectrum. So using the high energy parts as the photon energy to split the water, and using the rest of it that's not using to directly excite the semiconductor to generate heat, to see if that can improve the efficiency of the process. So what you see here is a short video of a photocatalyst sheet when I'm working with Kazunari Doman from Japan. This is his photocatalyst sheet. This is a video taken in my laboratory where we wanted to see what would happen under concentrated light. And as you see here, as you increase the amount of this is just a UV LED. As you see, you increase the intensity of the LED, you can see more and more bubbles of hydrogen and oxygen coming off. So this is the commingled gas coming off. If you plot this as a function of time, you can see that as you increase the photon density, then the slope of this production curve gets steeper and steeper. So clearly these materials are responsive to increasing amounts of light illumination, and we would think solar illumination as well. So if you now plot the production rate as a function of this photon flux, you see that you get this curve. Well, it starts off being a straight line. It does sort of tail off as you go up to higher intensity, but clearly there's an increase in production rate as an increase in intensity. But what we also found is if you increase the temperature of this reaction, and you can see here now we've got the hydrogen production rate against photon flux for different temperatures. The red data points are at 23 degrees. When we increase to 35, 50 degrees, we get an increase, a further increase in the production rate. And even when we go beyond the boiling temperature of water up to 120, we're getting even higher production rates occurring. So clearly what this is demonstrating is that there's an added bonus to bringing in the rest of the solar spectrum to generate some heat as well. This work has just recently been published, and it was identified as a hot article in the journal that we published in, something called Ease Solar. It's freely available if anyone wants to check that out. So it's open access. Okay, thinking about this though, what my group has done is started to consider the possibility of using photocatalytic water splitting under concentrating solar conditions. We have a lab simulator that can test up to 500 suns. So this is ongoing testing that we're doing. We're developing new reactors because this needs different types of thinking. We've produced a patent, and this led to engagement with industry partners to think about scaling up this technology, this idea of using photocatalysis under concentrated light. And that led to the development of Spark Hydrogen. Now, I'm not going to talk about the work that Spark Hydrogen is doing. That's going to be Vinod coming in after me. He's the project manager for the project, and he'll talk a bit more detail about what Spark Hydrogen does. But what I want to do is continue talking about what's happening around the world where people are thinking about photocatalysis and perhaps also photocatalysis under concentrating solar radiation. So again, this year, this work came out of a Chinese group where they thought about using photocatalysis under concentrated light, just like we have. But the excess energy, they are thinking about using it to drive a Rankine cycle for electricity cogeneration. So it's really a model type paper where they're saying that, again, the high energy photons are used for photocatalysis, and these near infrared and infrared photons can be used to heat up a fluid, and that can be used to drive a Rankine cycle. It does not go into details about what the reactor is, and I would dare say that they would be impinging on our IP if they did start to develop those sorts of reactors. Another way that we can think about improving the efficiency, and this is again some work that's come out of my group, is the idea of not using those infrared photons to produce heat, but to do this magic trick where you combine two lower energy photons to produce one photon at a higher energy. This trick has a very fancy name. It's called triplet annihilation upconversion, where you can take, for example, light at 450 nanometers and produce ultraviolet light. And that's what we did in this paper. Again, it's just come out in the last year, where we used a upconversion system to drive overall photocatalytic water splitting. So this is the first time that such a type of upconversion system has been used to drive photocatalysis. And we found that hydrogen production doubled when excited at 455 nanometers and tripled at 470 nanometers. So normally this material, this semiconductor, photocatalyst material, would not be absorbing these wavelengths, but because of the upconversion, we were able to drive photocatalysis. The nice thing about this approach is that near infrared to visible upconverters are very efficient. So if we get to the point where we would be using a visible active photocatalyst, then we could start to use those near IR photons and upconvert them into the visible. These are very, very efficient. The other nice thing about this is it couples nicely into the idea of using concentrated light, because this upconversion process actually improves efficiency under increased concentrating light. Techno-economic assessments. For photocatalysis, they've been around a while. Let's see here, way back again over 10 years ago. This first paper that was published by a group of people who are still involved mostly in the US have come up with 4 different types of ways that they could think about scaling up photocatalysis, where you just have these suspended particles in these bags. This is a so-called baggy system. So you've got a particle suspension, you've got one where they're separated, then you've got another one where you make these fixed array panels, and you've got one where these fixed arrays are irradiated by concentrating light here. And they identified that the final cost varied from between $1.60 a kilogram up to $10.40 a kilogram. Just go here, you can see for the different types, you can see they've got different costs. And you see for all of them, what was learned really from this work is that the capital costs are a significant proportion, a significant contribution to the overall levelized cost of the hydrogen there. Here we see some tornado plots. And again, what you see, that perhaps not surprisingly, is that it's the efficiency which has the biggest uncertainty. So the higher you can make these photocatalyst particles in terms of efficiency, solid hydrogen efficiency, then you're going to end up with a cheaper levelized cost of hydrogen. And all of the subsequent TEAs, so there's been perhaps a handful of them over the past decade, have all been based upon these 4 different approaches. So pretty soon after that one, there was a life cycle assessment done, and they calculated an energy payback time, which is 8.1 years, and the energy return on energy invested, ERO, is about 1.7. Again, you can see a tornado plot showing that solid hydrogen efficiency is very, very important component here. But that EROEI ratio of 1.7 sort of falls below what's reasonably thought to be the minimum needed for a commercial system 3. And ideally, you want your payback time less than 10 years, which it is. So this was the only life cycle assessment that had been done on photocatalysis until just earlier this year. This other paper was produced. It used, again, one of these models. It used the baggy system, where you can see that the levelized cost of hydrogen significantly decreases as you increase the scale of the plant. So that's 1 million tons going up to a 50 million ton plant, significantly dropping in price. And again, you see that here the price as a function of the solid to hydrogen efficiency. So really starting to come down to these mouth-watering low numbers that we're all hoping to achieve. But once you get to these higher solid to hydrogen efficiencies that are approaching what we think is the theoretical maximum. They also calculated the EROEI 2.47, so closer to that 3 now, and with an energy payback time of 16.2 years. Now, there are very, very few of these studies out there. It's something that I think there should be more attention paid to. But if you go looking for them, don't be surprised not to find them because they just don't exist. There's maybe a handful of them. And one of the reports I'm writing for the IEA that I'm involved with, the subtask, I'm incorporating all of these into a report that should be at least the interim report will be available by the end of the year. All right, you can't go anywhere these days without hearing the word AI. And in fact, one of the places that AI certainly has been touted to have an impact is in the development of new materials, specifically for new photocatalysts. And already there has been a more than a smattering of papers that have been published on people using machine learning or AI for developing new photocatalyst materials. The question that I'd ask myself is how long until this is an impact? But in fact, this is already happening. So here's a paper published in 2020 where they used a mobile robot. There you see it here. It was integrated with a routine for improving the photocatalysts, and the robot operated autonomously over 8 days, did 688 experiments, driven by a search algorithm, and over that 8 days, it developed a photocatalyst that was 6 times more active than the initial formulations. So you can see the hydrogen evolution starting from down here, increasing by a factor of 6 over those 8 days. Now this is already quite old, this approach, but I have no doubt that this is where the future is going to lie in development of clever routines for identifying what people have done around the world and trying to come up with better and better photocatalysts. And this way we're going to be inching slowly, perhaps slowly, but surely towards that theoretical solid hydrogen efficiency of 30%. I want to make another point for those of you that are going out there looking at papers on photocatalysis is people often report hydrogen production, but it's the oxygen production that is thought to be the more difficult reaction. And so people have been coupling hydrogen production with a different type of oxidation reaction. So here's a paper, for example, that did the oxidation of some exotic organic material. It doesn't matter what it is. They've even scaled it up to a relatively large size. Now, the problem with these sorts of approaches is this is relatively easy to do. As soon as you are not producing the oxygen, this is very easy. But the question, what you have to realize is that how much of these other oxidation products do you really need? And I put it out there that there is no oxidation product apart from oxygen that scales with the needed amount of hydrogen in the world. Nothing else will scale to give you the amount of hydrogen that you need for those 100 million tons, for example, with one exception. And that is utilization of photocatalysis for wastewater treatment. Now, people do use photocatalysis for treatment of wastewater, and this is one where it would scale. So you could produce a large amount of hydrogen, and because there's a large amount of wastewater that needs treating, that is the one that would scale. Okay, I told you I'd come back to the HILT forum. So here it is. Those of you who are interested in all different types of hydrogen production, I encourage you to get involved. This is all online. I'll show you on the next slide. Anyway, so it's going to be held in late October. Here are all the different technologies that we're covering. So these are all generally recognized ways of producing hydrogen, including large-scale commercial electrolyzers. What I've spoken today mostly about is this photoelectrochemical and photocatalytic route. But what I thought I'd also just briefly touch on is these hydrogens from natural gas or methane pyrolysis and these redox thermochemical processes here. So if we look at the carbon intensity for different types of the colors of hydrogen, which I assume you're at least vaguely aware, you'll notice that there's this interesting turquoise one that has a relatively low carbon intensity, certainly compared to gray and black hydrogen. So what is this? This is the thermal cracking of methane at a relatively high temperature. There's a number of different ways you can do this, but clearly it's in the absence of air. So rather than producing carbon dioxide, you only produce solid carbon. Now, because of the mass of these atoms, you actually produce 3 kilograms of carbon per kilogram of hydrogen. So there is an issue in this field about what to do with all the excess carbon. People are making fancy carbons like nanotubes and carbon fibers for it. What is very important about it is that it requires about half the amount of electricity that electrolysis requires. So you could very easily see that you could have a lower cost of hydrogen. In fact, if you're using biogas as the feedstock, you end up with negative emissions, and people clearly think that the goal is about $1 a kilogram for hydrogen. I'm just going to mention two companies, an Australian group you possibly heard of, Hazer Group. Their carbon product is magnetic because it's got iron as part of the catalyst, and they have a feed study completed on a Canadian facility to make 2.5 kilotons of hydrogen per annum. And I'm not sure, I think that FID has now been made. The other company is Monolith, based in the US. They built their first facility called Olive Creek back in 2020. They are now constructing their second facility, which will have a capacity of 58 kilotons per annum. And this, I put it to you, would be a good size, for example, for a regional industry hub. Now, there is one caveat with this approach. Because it uses methane, you cannot afford to have any upstream fugitive emissions of methane. The leakage you need to have below 0.4%, and it's currently estimated to be above 1%, at least by the US EPA. That was before they were gutted, so let's hope they can still able to do their good work. And there are a lot of companies emerging in this space. Here's a list that I got from my colleague, my hyped colleague, working in this space. A lot of people are working in this space, so it's one to watch out for. All right, the second approach is thermochemical approach, where you take a metal oxide, you heat it up with concentrated light, you partially reduce the metal oxide so that you lose oxygen, then you bring in water. This material takes up the oxygen and leaves you with hydrogen as well. So you're cycling through the temperature. However, this has proven to be difficult, and focus has turned to other different types of chemistries involving carbon and sulfur that seem to be easy to occur and can happen at lower temperatures. And one of note is, for example, a company called Synhelion, where they are using biogenic CO2 and water to produce syngas, and then subsequent Fischer-Tropsch synthesis to produce jet fuel. They are now producing jet fuel, and if you look them up on their webpage, you'll see that they've driven on other things like the first flight, the first motorbike, etc. Their solar to syngas efficiency is about 4%, and the fact that they're using thermal energy storage enables their plant to operate 24 hours a day. All right, I just want to finish off with 2 case studies where I think that going back to direct solar hydrogen could be useful. Here's a map, came out now a few years ago now from Advisian, looking at all the different sites that utilize hydrogen. The big one, of course, is this one out here in the Burrup Peninsula, Yarra Pilbara Fertiliser. Their one plant produces 840 kilotons of ammonia per annum. That one plant is 5% of the global market. Just about all of that product is exported on the export port right there. Located next to the natural gas field, obviously that hydrogen comes from steam methane reforming. So I put it to you, there's a good solar resource here in the Pilbara. So you could generate your hydrogen with very minimal storage, drive that or make your so-called green ammonia here. The other one is, since we're in the HILT CRC, I did an early project looking at CO2 coming from 19 different plants, which contribute 10% of Australia's CO2 emissions. What's of interest is the cement and lime plants. These are fixed and they're continuous sources of CO2, and they could very readily provide a feedstock if you wanted to need carbon to react with your hydrogen to make a chemical feedstock. Okay, that's the end of my presentation. This is me over the last few days dabbling with AI, trying to get an image of how concentrated photocatalysis could change the world. With that, I'll hand over to Vinod, who'll talk a bit more about spark hydrogen.
Thank you very much, Greg. Just hoping Vinod can share his slides. It looks like it's going well. Excellent.
Yep. Can you see that?
Fantastic. Please go ahead. That we can see that, yes.
Thank you, Fiona. Thanks, Greg. That was a prelude, a good one to introduce what technology that is going to be involved in spark hydrogen's introduction that I'm going to do today. Just a little bit of background. The technology was actually developed at the University of Adelaide by Professor Greg Mehta's team. And it was envisioned at the time that there's potential for it to be a commercial product. So 3 companies, Spark Technologies, Fortescue, and the University of Adelaide, came together and decided that a spin-off company, Spark Hydrogen, would be formed. And this company is set up mainly with the mission of developing the next generation green hydrogen using the photocatalytic water splitting technology as its base. I won't go too much into the technology. I think Greg mentioned exactly how the photocatalyst works, the whole process of splitting water into hydrogen and oxygen. But I would say that the key breakthrough in this field, which we think will ultimately deliver low-cost hydrogen production, is mainly on the reactor. We have the patented solar reactor that's exclusively licensed to spark hydrogen. And we're also using the concentrated solar fields, which are becoming a more mainstream equipment that's being used all over the world for thermal heat production and storage. And that's the reason why the price of concentrated solar fields are coming down, and that adds to the benefits for our technology. And also, as Greg mentioned, the theoretical efficiency of photocatalysis is still very high from where we are at the moment. So there's going to be a lot of opportunity to constantly improve the photocatalysts that we will be using in our system. So the reason why we are doing concentrated solar instead of just using a single sun approach, as Greg also mentioned a little bit earlier, we do concentrate a large area of sun into a smaller area concentration, which means that we only need to use a little bit of photocatalyst at the concentrated area instead of the whole large panel area. So that kind of saves a lot of cost in terms of photocatalyst that's being used. And it's also able to be integrated with existing solar concentration systems. We don't need to reinvent the wheel and make our own concentrated solar systems. And also, we obviously can get a lot of benefit in terms of the byproduct heat that we get out of the concentrated solar system. Our reactor has been improved over many evolutions, and we also have a patent that has been granted to one of our designs at the moment. We are waiting for a few other patents to be granted in about 18 jurisdictions in the world. And being a pioneer in this field, our reactors are actually going to be leading the field as far as the technology goes. We have a good team that's working on the research at the University of Adelaide, and also with Professor Gunther involved in the project as well from the early days with Professor Greg Mehta. There's about a team of 3 senior researchers and 2 PhD students working under Greg. And I think that adds to the benefits to Spark Hydrogen, having a good, strong research team, aside from the industry partners within Fortescue and Spark Technologies, also giving their contributions as required. So the technology that we actually brought from the lab was scaled up to a prototype version, so about 30 centimeters by 30 centimeters size. And that was tested at the CSIRO Energy Center in Newcastle in March of 2024. It was the first demonstration of the technology outside of the laboratory, and produced vital information, which allowed us to learn a lot about real-world application, and we have managed to improve the design of the reactor. We had a Mark II reactor prototype that was also built and tested at CSIRO, and the overall outcome of that testing was quite encouraging. And due to that, we actually decided, the joint venture decided that we should proceed with a pilot demonstration. To that end, we managed to secure a site in Roseworthy at the University of Adelaide's campus at Roseworthy, and we built a pilot plant. It's still under construction. At the tail end of construction, it should be up and operational by mid of August this year. The pilot plant is using a commercially available concentrated solar mirror. We purchased the mirrors from a company in Spain. They are quite readily available, and they don't cost a lot to purchase. The benefits that we get from this pilot plant is also, it allows us to de-risk the development of the established operating conditions for a larger commercial scale plant. It is also, we foresee this facility being a global leading facility for R&D and commercialization of photocatalytic water splitting, which allows us to test other different designs of reactor and photocatalyst material. It also has the potential to solidify Spark Hydrogen's leading position in the development of concentrated solar-based water splitting reactor, with the ability to test under real-world conditions. The 2 photos here show concentrated solar fields using linear Fresnel mirrors. The idea is to have a modular system that we can tack on to make it as big or as small as we want. As you can see in this photo, this 30 megawatt electricity plant takes up about 28 by 1 kilometer mirror rows to produce 30 megawatt of electricity. So in terms of the use case, obviously, our main comparison here is Spark Hydrogen photocatalysis to solar PV electrolysis. So they are both good for places where we can utilize the high solar resource. But other than that, Spark Hydrogen's photocatalysis system can be more remote and off-grid oriented, because we don't actually use the grid power as you would require the photocatalysis, sorry, the electrolysis plants to apply. We are also a bit more scalable, and as I mentioned earlier, the linear phenol mirrors are modular, so they can be tacked on to as big or as small as we want. And the other thing that we look at as a benefit is the fact that gases that are being produced are commingled, which is hydrogen and oxygen. So if we are looking at a combustion use case where we need high temperature heat, the gas can be actually combusted with the mixture of oxygen and hydrogen to get high temperature heat. And also the benefit of using concentrated solar, we have industrial co-production of heat, which we can use for any other use case within the offtake. So if someone actually requires hydrogen at a plant that's also needing low-grade heat, then a system like ours will be very beneficial for them. So in the short period of time since the Spark Hydrogen has been established, I think we have done pretty well, having completed a prototype testing at CSIRO within 2 to 3 years. And now within 3 years now, we are already at the stage of constructing a pilot plant. Having a pilot plant is a very big benefit, not only for research in the field, but also because it allows us to showcase the ability of the technology to actually produce something commercial and can be used as a track record when you're looking at operational ability of the plant. Yeah, that's a very short introduction to Spark Hydrogen. We didn't have a lot of time to talk about the plant any more than that, but feel free to ask any questions if you have specific questions that you would like me to talk about. Thank you.
Thank you very much. Really interesting presentations. Really nice to see that link between fundamental research and right up to pilot plant and pilot scale demonstrations. So fantastic. We did have a presentation, a question on the presentation around contaminants. So the question in particular was what kind of contaminants degrade the photocatalysts and cause their performance to drop off. And if I can take the opportunity to just expand that a little bit, to ask you to talk a little bit about lifetime of these types of photocatalysis materials and how often they need to be replenished.
Yep. Thanks, Fiona. Well, I'm sure you could have handled the contaminants question. So as I mentioned before, that indium gallium nanowires had been shown to be reasonably efficient using seawater. So I would have thought that any dissolved ions would be relatively benign to photocatalysts. What would be the killer is organics. So if you had any organic material there, you'd reduce it, and the difficulty would be that you'd end up with a big lump of carbon that would block those catalytic sites. So look, there's not a lot of research in this field. People typically use deionized water, or certainly relatively clean water. So I don't think you could be using, look, you could possibly use seawater and maybe even bore water, but when it comes to organics, I think we want to steer clear of that. In terms of lifetime more generally, I mentioned that the Domin's photocatalyst has been shown that even after 1,300 hours, so in the field, that would be about 9 months operation on sun, and it dropped less than to about 80% of its efficiency. The indium gallium nanowires has also similarly been tested to out to 1,000 hours. So these materials are starting to become quite appear to be quite durable. The organic material, the inorganic organic PEC device that I mentioned before from Imperial, that has started to grade after tens of hours. But look, that was early days for that one. So look, there are some that are fairly long-lived, and there's some shorter materials, and that's certainly going to be a challenge in the field. I liken these challenges all to what the photovoltaic field had to address 20, 30 years ago.
Yeah,
As somebody
and
wrote, more science, more funding for science.
I
Bubble
would
funds
I
up,
would
yeah.
second and third that myself. Yeah, and if I can just sort of add to that and say, we noticed, well, I noticed on your some of the techno-economic plots that, along with efficiency, lifetime is up there as one of the key factors as well. So an important challenge. We've got we have an off-piste question from Graham asking about the indicative levelized cost of hydrogen or turquoise hydrogen. So that's the methane pyrolysis. Any ideas, ballpark?
Yeah. Whenever I hear talk from them, they're always talking about the issue with the carbon. They never talk about the hydrogen. So look, I think maybe Murray might have mentioned $4 or $5 a kilogram at the moment. And
yeah,
obviously,
does that include some?
If that doesn't include the being offset by the carbon. Yeah.
Sorry, Greg. Apologies. It's always so difficult to avoid over talking each other.
Yeah, I know. Hazer, they're Australians, right? They should be letting us know these sorts of things. So
definitely. And one for Vinod by your namesake, Vinod Patel, who's asking how big is the Roseworthy pilot in terms of H2 production per day or year, and what is the overall efficiency? I don't know if either of these things are things you can share at the moment, but it would be great to get more details.
No, I can just explain that the pilot plant was not actually built to produce hydrogen for any use case. We're not going to we don't have an off-taker, so it's actually mainly for research purposes. It's a very small amount of hydrogen that we are producing. Based on the mirror size, it's about 100 to 130 square meter size. We are probably looking at a maximum at the top of the production time at a maximum of about 1 kilogram of hydrogen per day. So obviously throughout the year it varies, throughout the weather system it varies as well. We are not using a specific photocatalyst for the pilot plant. There's a varying options that we're looking at. If we get a good quality, high performing photocatalyst, it will produce the maximum, which is the 1 kilogram of hydrogen per day. But if we use a lower performing one, obviously it will be a lot less. Hope that answers that question.
Yeah, and I'm just going to add on to that as well. So one of the things I was wondering was, and I noticed your comparison between solar PV and the Spark approach. I was wondering if you have a feeling about land use requirements, and if you can assume that you've got like standard solar cell field and a standard electrolyzer, do you have a feeling of whether the Spark if you were producing the same amount of hydrogen, would a Spark facility be much bigger, much smaller? Do you have any idea? Do you have any feeling about that? How is it going to be a saving in land use?
We actually did a basic calculation, back of the envelope type of calculation would be about 70% of the land use if you're talking about the same size of electrolyzer coupled with PV farm. Obviously, we don't have a lot of the facilities that the electrolyzers will need. For example, switch yard for the grid and a few other things that we don't need to have in our system. Our system is pretty simple. It's just if you come up to the pilot plant, or if you have a look at the photos of the pilot plant, then you can see how simple the whole system is, and it's going to be a lot easier to assemble and produce hydrogen that way anyways.
Fantastic, really interesting. There was another question, will transport and distribution be an intrinsic issue here as well, or will the plants find best location only near user locations? I think this is an important question.
Take that, Greg.
Oh, Fiona, in your role in the HILT CRC, you could probably answer that, right? So.
Oh, I have opinions, but it wasn't at me.
Oh, look.
Yes.
Look, when you read people talking about the issues with hydrogen, transport and storage is certainly up there. It adds, you know, what, 30% of the cost to the hydrogen. So I think the lowest hanging fruit is going to be if we can build our plants, and the advantage, as Vinod was just saying, our plants don't require connections to the grid. So we could go in those areas with good insulation, solar insulation. And if they're located to those plants, which is why I picked on the ammonia production plant on the northwest of WA, I think they're going to be our lowest hanging fruit to go for.
Fantastic. And then we are on time. I've just realized I've been reading questions from the chat instead of the Q&A. So thank you, Adam, for copying things across. So Sandao, who's actually the research lead on the program 3 in the HILT, asks, what is the current challenges that the Spark Hydrogen pilot plant is aimed at shedding light on? And then says, no apologies for the pun.
Oh, this is going to be tough because we haven't actually completed the plant, so we don't know what other challenges that we're going to face. But off the cuff, we can say that some of the equipment that's needed, because this is like one of the kind plant that's being built anywhere in the world, for example, we don't actually have a solution for some of the equipment that we need. We are just going off the experience in the field at the moment. It's a lot of things are being analogous to oil and gas. So we're using equipment that is more suited for oil and gas applications, but you know, that are things that we need to fine tune as we go along for our next scale up purpose. And some of this equipment as well, they are not readily available in Australia. So when we are sourcing valves and transmitters and things like that, because they need to be intrinsically safe, because you're working in a hydrogen environment, there's some requirements, certifications that's needed that makes this equipment hard to come by. And sometimes we are waiting for equipment to come from overseas. It takes 6 weeks to 8 weeks to arrive. And you know, those are the main challenges that we've been facing as far as the whole pilot plant is concerned.
Fantastic. Thank you very much. I would just, you know, say, I think that one way of summarizing that is just the learning by doing. We really just, you don't know what you're trying to solve until you're actually doing it. And I think that's such an important part of the whole process. So I'm reluctantly going to have to close that there. Thank you very much, Greg and Vinod, for your time and your presentations. Really interesting, and lots of thanks and appreciation in the chat as well from our participants. So thank you again on behalf of the HILT CRC.
Thank you.
Thank you.
And this presentation will be recorded and hosted on the HILT CRC website. So please feel free to share the link if you have other people who would be interested in this conversation. Thank you.